Good morning. I hope you can hear me. So you may remember that we were considering the MOS photocapacitor. So in order to start again with this subject, I want to show you the figure showing the device. Okay, there we are. So you should look at the upper part of the figure here. We have the standard structure of a MOS capacitor. The only difference is that the upper electrode, the gate electrode, is much smaller than in the usual structure of the capacitor because we need to leave the upper surface of the device free from contacts as much as possible. You may remember we already discussed this issue when talking about the solar cell. And assume for an instant that there is no light, simply that you have a standard MOS capacitor in which initially the bias is corresponds to the flat band condition. So I change the figure for 1 second. I don't know whether it has become visible, but I'll do it immediately. So here you should look only at the curve, okay? This curve shows the evolution with respect to time of the applied bias. So we start at t equal to 0 with the value of the gate voltage corresponding to the flat band condition, okay? So Vg is equal to VFB, that means that Vg prime is equal to 0. And then we bring the gate voltage. We are in a p-type substrate, okay? We make the gate voltage more positive and bring it in a short time to a value that in steady state would correspond to the strong inversion condition. And the time, I don't know whether it is visible, I make it larger, the time that it takes to go from the flat band voltage to a high voltage is called TR, rise time of the gate voltage. Here we use the symbol VDD because it is a different set of slides, but it is a high voltage, okay, corresponding to strong inversion. Then we keep the voltage to a large value, okay, and then we bring it back to the flat band voltage, okay. So the duration in which V gate is high up to the time Tp is the integration time. and the time that it takes to go back to V of flat band, okay, brings the photocapacitor back to the state of flat band condition, but we shall examine this later. I simply just wanted to point out that this is called TF, it is the fall time, okay? In this figure, the raise time and the fall time are equal because in general, they are equal to each other, okay? Now, what are the lengths of the raise and fall time? They are much smaller than the lifetimes of the carriers, okay? So you remember that in a good piece of silicon, that means with not so many defects in the gap, the lifetimes tau n and tau p are larger than 1 microsecond. They may be between 1 and 10 microseconds. Okay, so they are relatively large times. The raise and fall times TR, TF are much smaller than the lifetimes, but they are in turn much larger than another specific time that is called dielectric relaxation time. We shall see in a minute what the meaning of the dielectric relaxation time is. We call it tau d, and tau d is the ratio between the permittivity of the semiconductor, in this slide it is called epsilon s, and the conductivity of the semiconductor. Okay, of course, the conductivity depends on the dopant. So if we take a typical value of the dopant in the range of 10 to the 15th or 10 to the 16th dopant atoms per cubic centimeter, then the dielectric relaxation time is in the range of the picoseconds. Okay, so it is much, much smaller than the lifetimes, and the raise time and the fall time are in between. So now we go back to the other figure. Here. And we assume that there is no light, and we bring the gate voltage from the flat band value to the very high value corresponding to strong inversion, okay? And this takes a short time, that is the raise time. What happens in the bulk of the semiconductor? It happens that since we are applying a positive voltage on the gate, the holes that are also positive are pushed away from the surface. And here the dielectric relaxation time comes into the game, because the dielectric relaxation time is the typical time that it takes to the holes to being pushed away, so that we form a depleted region, okay? This depleted region forms in a time that is of the order of the dielectric relaxation time, practically almost immediately, because that time is very short. So simply the holes follow the raise time. They just leave this area, this volume, depleted of charge, okay? But we do not have any inversion layer. Why? Because the lifetimes of the generation of the thermal generation term are so long that it takes a time that is much, much longer to form the inversion layer in the semiconductor. Remember, we are discussing a case in which there is no light, simply thermal generations, okay? Now, what are the typical relations that we can write down in the MOS capacitor in this case? We change the page. Here. And we take the typical relation, you remember, that occurs between the inversion charge in the semiconductor, the total charge in the semiconductor, and the charge associated to the bulk charge, okay? We already have examined this page a few lessons ago, but I come back to it now. It is very easy to calculate the value of the surface potential. We simply invert the algebraic relation between charge per unit area in the inverted layer, that is Qi, the applied voltage, the gate capacity, the oxide capacitance, and the surface potential. So we find an easy relation between the square root, you can see it in the first line, a square root of the surface potential in terms of the applied voltage, Vg prime. You remember Vg prime is the gate voltage minus the flatband voltage. The absolute value of the inversion layer and the oxide capacitance. Gamma, you remember, is the coefficient that appears in the relation between charge and surface potential. We may have this relation where is it? Here. This one, okay? Near the bottom, you can see the general relation between the inverted layer charge and the rest of the parameters. We simply invert this. And what we find is this. As usual, this relation alone is insufficient because there are essentially two things that are unknown. One is Qi and the other one is phi s. So in order to find independently phi s and then from it to calculate Qi, we must consider the general relation, those that are much more complicated for the MOS structure that we found by integrating the Poisson equation, okay? But for the moment, we are happy with this. So what happens when we pulse an MOS capacitor? We open up the depleted region, but we do not have any inverted layer. So we simply apply this relation by letting Qi equal to 0. Okay, so at the very moment when we apply the pulse, Qi is 0 because there has been no time to form the inverted layer. So you see immediately that when Qi is 0, Vi is the maximum because of the minus sign here, okay? So Vi becomes equal to Vg prime. So at the time of applying the pulse, phi s is the maximum, okay? Let's call it phi g, okay? So phi s is much, much larger than the equilibrium value. The equilibrium value is reached after a time when the inversion layer has formed, okay? Since there is no inversion layer, the total charge in the semiconductor is due only to the charge of the depleted region. That means also that the extension that we usually call XD of the depleted region is much larger than in the equilibrium condition. So XD, at the instant in which we switch from V of flat band and the high value of the gate voltage, is given by this formula, XD equal to this coefficient times the square root of phi g, and XD is much, much larger than the equilibrium value. At this time, due to the thermal generation, the inverted layer starts forming until the device reaches the equilibrium condition. At equilibrium, the variation with respect to time of phi s and xd stops, and they reach the equilibrium condition. Now, let's go back to the photocapacitor. What is the difference between the photocapacitor and the capacitor? The difference is that we have in parallel two generation phenomena. One generation phenomena is due to the thermal generation, and the other generation phenomenon is the optical generation. So we have two causes for generating the inversion layer. All these generation events correspond to the formation of an electron-hole pair. And as you remember, in the depleted region, there is a strong field. So the electron and the hole separate. The electron is attracted to the surface and the hole is pushed into the substrate. So eventually we form the inversion layer. If the optical generation is dominant, the majority of the electrons that are in the inverted layer have been generated by the light. So we have somewhat a layer of electrons that is mostly due to the optical signal impinging onto the sensor, okay? So at some point corresponding to the end of the integration time, we bring back the voltage on the gate to the flat band value. And what happens is that we practically eliminate the vertical field in the space charge region. Okay, there is no field left in that region, so the holes go back and flood completely the space charge region. Okay, so the holes fill up all the space charge region, and the vertical field is eliminated. The layer of electrons is not attracted anymore near the surface because there is no field anymore. Okay, so there is a layer of electrons that is initially attached to the surface with no field keeping it in place. So these electrons, of course, they start diffusing into the substrate. Okay, so the electrons diffuse into the substrate, and at the same time they recombine with the holes. And this mechanism of diffusion of the electrons into the bulk attracts or produces a current that flows into the load resistor. So at this point we can read the current through the resistor. How long does it take? It takes the time that is necessary for this layer of electrons to disappear, okay, the time that is necessary to restore the equilibrium condition in the device, okay? And this is the sampling time. So the sampling time may be long in this device because we need that all these layers of electrons recombines completely with the holes, okay? So it is necessary now to understand how long is the sampling time, okay? Because the sampling time, of course, should be as short as possible, okay? Because we want to start integrating again the signal of the device in the next, for the next signal, okay? So the next analysis is a calculation of the duration of the sampling time for the MOS photocapacitor. This is relatively easy because we solve the electron continuity equation, okay? As usual, we must account for both the thermal recombination U, and for this we assume the weak injection condition, so that the equation is linear with respect to n. And then we must consider the optical generation, and as usual, as you can see here in the text, G is equal to Gs times the exponential of minus Kx. As we did in other occasions, we consider a monochromatic light, which of course is not true, okay? The light is not monochromatic. So in principle, what we should do is, considering one frequency, make the calculation for one frequency and then sum up over the frequencies, okay? Now, what happens of the divergence of Jn term, okay? First of all, it becomes one-dimensional. So the divergence of Jn becomes the derivative of Jn with respect to x, okay? And then we take the equation and we integrate the equation over the device. That means between the interface between semiconductor and oxide, and as usual, that is the point x equal to 0, to the bulk. The bulk is at infinity. So we integrate the equation, the continuity equation, from 0 to infinity. The first term, the derivative of n with respect to t, can also be written as the derivative with respect to time of n minus np0, okay, because np0 is a constant. When we integrate it, we obtain, as you can see in the middle of the page, the derivative of the integral from 0 to infinity of q times the excess electron concentration with respect to the equilibrium value, okay? Let's call it Q, okay? So capital Q is the integral of the electron charge Q times n minus np0 integrated between 0 and infinity. This is capital Q, okay? So the first term gives you the derivative with respect to time of capital Q. Then we have a term associated to the thermal generation or recombination. In this case, it is a recombination, of course, because n is larger than np0. We take the weak injection condition, so U is n minus np0 over tau n. So after multiplying the continuity equation by Q, we have simply capital Q over tau n. And then the other term at the left-hand side is the derivative of Jn with respect to x that we must integrate between 0 and infinity. So we get Jn at infinity. In principle, it is not infinity, it is L. L is the total thickness of the semiconductor wafer, okay, which is almost infinity for these purposes. So we integrate between 0 and infinity. But obviously, at 0, there is no current because no current can cross the interface between semiconductor and oxide, okay? So Jn at 0 is 0. Jn is non-zero in the bulk, but as we said before, the electrons diffuse into the bulk, and at the same time they recombine with the holes. So this population of electrons becomes smaller and smaller as long as when we go deeper into the bulk. And at some point, this population of electrons becomes negligible. So the current at infinity is practically equal to 0, okay? And then we have the right-hand side. The right-hand side is the integral of G. Obviously, it is proportional of the exponential of minus kx calculated at 0, that gives you a 1, minus the exponential of minus kx with x equal to L, capital L, that is practically equal to infinity. So this exponential is 0. So as usual, the integral of the optical generation term reduces to a constant, okay? So in conclusion, we obtain a differential equation with respect to time that is immediately integrable. The integration is shown in the midsection of the page. It is like having derivative of q times the exponential of t over tau n equal to q gs over k again times the exponential of t over tau n. So when we integrate this equation, we obtain that the charge per unit area, capital Q, associated to the excess electron concentration decays with respect to time. We expected that, okay? Because we have at the right-hand side the exponential of minus t over tau n. The quantity in parentheses is, of course, the value of this excess charge at t equal to 0. You can notice that the excess charge Q does not go to 0 when time goes to infinity, okay? It goes to Q tau n times Gs over K. So why is it so? Why does not the excess charge go to 0? Because the light keeps coming. So we still have generations in the material. This generation have never been stopped, okay? So since we have generations, when time goes to very large values, essentially the generated charge that is represented by Q goes to equilibrium with the optical generation term, okay? Only if Gs becomes 0, so if we put the light off, then the excess charge Q of T will go to 0 really, okay? Some of you may argue that the optical generation term must depend on time. In fact, it does. G sub S depends on the illumination that comes into the device. So this illumination may change with time, okay? So why did not we consider this in the calculation? Because we assume that this change with respect to time is slow with respect to the internal times of the device that are essentially the lifetime of the minority carriers tau n, okay? So we neglected the variation with respect to time of the illumination, okay? Conclusion, the asymptotic condition of the excess charge is dominated by the minority carrier lifetime tau n, and tau n is not very short. You remember, tau n may be of the order of 10 microseconds, okay? So that means that the sampling time may be excessively long, okay? So this photocapacitor by itself appears to be a slow sensor, okay? Can we improve it? Well, it is really easy to improve it because we can consider another architecture that is the one that is here, shown here. It's simply manufacturing change that is visible in the figure. We start, instead of starting with a p-type substrate, we start with the N+ type substrate, so a very heavily doped substrate of N type. And then on top of it, by a suitable technological process that is called epitaxy, it is indicated in the label on the left. It's an epitaxial process. We grow a thin layer of the p-type on top of the N+ substrate. Okay, so where is the difference? The difference is that the thickness of the p-type region is L prime. You can see it on the right, okay? And L prime is much, much smaller than the total thickness of the silicon wafer, that is L, that is visible in the upper part of the figure, okay? So the orders of magnitude is that L, the total thickness of the wafer, may be in the range of 0.5 millimeter, let's say 300 microns, okay? Instead, the thickness of the epitaxial layer, L prime, is something between 5 and 10 microns, okay? So it's 300 in the first case against 5 to 10 microns in the second case, okay? The N+ region that is below is very heavily doped, so it is very conductive. It is similar to a contact, okay? So using the N+ doped region below, it is like we have uplifted the position of the bulk contact from the original 300 microns away from the interface to a distance 5 to 10 microns away from the interface, okay? All the rest of the functioning of the device is just identical to the other one, okay? So we apply a large bias to the gate. We open up a depleted region that is visible here. Of course, the scales of the figures are completely non-realistic, okay? So the actual thickness of the oxide would be invisible in this scale, okay? And the distance of the thin line that marks the position of the edge of the depletion region is much, much closer to the interface than shown in this figure here, okay? But the functioning is just the same. So the inverted layer forms due to the combined effect of the thermal and optical generations. And then when we apply a voltage that is equal to the flat band, so we bring the gate voltage down again, we make the layer of electrons to diffuse, and they have to diffuse for a much, much shorter length, L prime, until they reach the heavily doped region. At this point, this heavily doped region is like having a contact here, and this is it. The electrons are absorbed. What is the difference in the calculation between the first example and the second example? The difference is that in the first example, the standard photocapacitor, we have that the inversion layer disappears because of the combined effect of diffusion and recombination. In this other case, we have a boundary condition for the electron that is very, very close to the interface, a few microns, okay? So we do not have infinity anymore. We don't have an asymptotic condition anymore. So we must solve the continuity equation with a different boundary condition. This makes it a little bit more elaborate because of this, but it is still doable, and we shall do it now. So in the epitaxial, when we have the photodiode, the photocapacitor in the epitaxial layer, we define, as before, the excess charge per unit area, just as we did in the other case, but you see the integral is extended not to infinity, but to the thickness of the epitaxial layer. This thickness here is called A for simplicity, instead of calling L prime, okay, because the symbol L prime is awkward, okay. Then we have the continuity equation, and the continuity equation must be solved without neglecting the term with the current density, okay, because there is no asymptotic condition anymore. However, we can consider that the expression of the current density for the electrons is essentially diffusive, because you remember, when we bring back the bias to the flat band voltage, we eliminate the field, the vertical field in the device, and the electrons move only by diffusion. So we can immediately eliminate the drift term of the transport equation for the electrons and keep only the diffusive term. So we have the derivative of Jn is equal to the derivative of Qdn times the derivative of the concentration with respect to n, okay? What are the boundary conditions of this equation? The boundary conditions are that, look at the central line here in the page, okay? The asymptotic condition does not exist anymore. So we must impose a condition at a finite distance A from the surface. And we impose a very reasonable condition that the heavily doped region of the substrate forces a condition of equilibrium to the concentration, that is, N at A at every instant of time is equal to NP0. Then we have the initial condition, because we have a differential equation in which we have the time derivative, okay? The initial condition is simplified in this way. We assume that at time t equal to 0, that time is the time in which we are switching the gate voltage from the high value to the flat band value, okay? This is t equal to 0 for this equation. The excess concentration of the electrons is a layer at the surface. So this layer can be described as a Dirac delta. So this Dirac delta is centered in the origin. So we have delta of x, okay? As usual, we have a factor 2 because we take only 1/2 of the delta, that is the half part that is inside silicon, okay? And then the integral of it must be equal to the excess charge at time equal to 0. So it is the initial condition of Q, okay? And finally, since the equation with respect to space has the second derivative of n with respect to x, we need another condition, okay? And this other condition is, for instance, the derivative of n with respect to x at any instant of time at the surface. And since the delta is, you know, the Dirac delta is not a function, but you can think of it as something that is even with respect to x, okay? So the first derivative is is 0, okay, because delta is even. So these are the boundary and initial condition for the equation to be solved, okay? The equation is linear, and obviously by some trick we can simplify it. And the first trick is that if you look at the first two terms, derivative of n with respect to t plus n minus np0 over tau, we find immediately an integrating factor for this part of the equation, that is the exponential of t over tau n. So because of that, we can introduce an auxiliary function that we call small f. So this auxiliary function is defined as n minus np0 times the exponential of t over tau n. Okay, when we replace this, the first two terms become derivative of f with respect to t divided by the exponential. Okay, so we bring the exponential to the other side. Then the derivative with respect to x is not influenced by this definition. So we can simply use f instead of n. And then we bring the exponential with respect to time to the right-hand side. So we have plus gs exponential of minus kx plus t over tau n. So we have simplified a little bit the equation. Of course, since we have changed the variable, the unknown function, we must now consider the new boundary conditions for f, but they are easy. The initial condition is again a delta by construction, okay? Because when we place t equal to 0, we have that f at time 0 is equal to n minus np0. And the condition in space are that f at a is 0, and the derivative of x with respect to sorry, the derivative of f with respect to x at the surface is also equal to 0. Okay, so we have to solve this equation. Okay, so this equation can be solved by series. Okay, so we make a trick. The trick is as follows. We are looking for a function defined between 0 and a, okay, in a finite interval of space, okay? The question is, we don't have time to complete the solution because we are near the end of the hour, so I just tell you the trick. We have an equation to be solved in a finite interval, 0 to a. Can we express the unknown function f as a Fourier series? Well, yes, because you remember, if you assume that a, or maybe half a, or whatever, is the period, the Fourier series will replicate the function outside the period. But what happens to the function outside the period is really of no concern to us, okay? Because we simply want to solve the equation in a finite interval, okay? So it is sufficient at this point to consider the Fourier series in the finite interval and check whether the series fulfills the initial and boundary conditions for the function f, okay? Then what happens to the series outside the interval is of no concern, okay? So what we do is we replace f with the new function that we call f hat, that for convenience is defined in a somewhat larger interval that is between minus 2a and plus 2a. So it is in a larger interval than the one that is of interest to us. And then we shall force f hat to be equal to the actual unknown f in the interval of interest between 0 and a, okay? And then, since we have some freedom in the selection of this function f hat, we impose that in the larger interval between minus 2a and plus 2a, this function is even. You see, when f is equal to minus, when x is equal to some value minus x, then the function is equal to the corresponding function f at plus x, okay? So we impose that f is even on an interval of length 4a centered at x equal to 0. Okay, obviously, if we express in a Fourier series a function that is by construction even, we have only 1/2 of the terms, those that contain the cosine terms, okay, and we do not have the sine terms, okay. So we know by construction that f hat can be expressed with some Fourier series that is shown here, in which the coefficients are only of the form of the cosine, okay? So hat g is cosine of k is of course the index, it goes from 0 to infinity, k pi x over 2a, okay? Where is the trick? The trick, as you remember, is that the Fourier series is is a sort of separation. Okay, you see that the space part of the function now it is known because the dependence of hat g on x is given. Okay, the coefficients hat c of t, they are the real unknown. Okay, we are separating the equation. At this point, we have to find these coefficients. Now we stop for 10 minutes and we shall calculate the coefficients in the next hour. Okay, so we start again. Let me go back to the analysis. Okay, there we are. Okay, so we essentially have separated the problem introducing this new function f hat expressible as a Fourier series. So we have a complete knowledge about the space coefficients, and we are left with the need of calculating the time coefficient c hat of time. Does this function f hat fulfill the boundary condition? Of course, it does fulfill the boundary condition in the origin, because f hat is made only of cosine functions, and the cosine is, as you remember, even. So f hat is even, so it fulfills the condition that the derivative in the origin is equal to 0. But it does not fulfill the boundary condition on the other side. It should be f hat of a equal to 0, and it is not, okay? But we still have a degree of freedom, because this function f hat is defined in an interval that is 4 times longer than the interval between 0 and a, where we actually need to solve the equation, okay? So we can impose another restriction. We can restrict the choice of f hat to a subclass of functions that are odd in the interval of length 2a that is centered at x equal to a, okay? Obviously, if a function is odd in an interval of length 2a centered at x equal to a, it will be 0 in the middle. So it will be 0 at point x equal to a, okay? And it will still fulfill the other boundary condition at 0, okay? So we simply restrict the choice, imposing that f hat of 2a minus x is equal to minus f hat of x. That means it is odd in that interval, okay? But this restriction immediately reflects into a condition on the coefficients, because we must simply impose that g hat of 2a minus x is equal to minus g hat of x, which means that the cosine, if you replace into the definition of g hat, the cosine of k pi must be equal to minus 1. So imposing this restriction is simply equivalent to impose a restriction on the indices k. These indices must be odd, okay? So we introduce a new symbol g without a hat, that is the selection of the g hat coefficients in which the index is odd, okay? We define gi equal the cosine of I plus 1/2 pi x over a, okay? And then we find the coefficients ci of the expansion, okay? We don't find them, we have the formal expression of these coefficients that is written at the bottom of the page. It is 2 over a times the integral between 0 and a of gi. Gi is given, is the cosine that is visible. before it times f hat. So now the issue is to find the time dependence of this coefficient Ci. So we now have the Fourier expansion in the final form. And you can see that in the argument of the cosine, we have a quantity that is I plus 1/2 pi x over a. Of course, this argument is the inverse of a length. So for compactness, we introduce this symbol 1 over capital Li, that is I plus 1/2 pi over a, okay? And we see immediately that G prime is the cosine, essentially, okay? So G prime at 0 is 0, G at a is 0, and G second, the second derivative of G, of course, is minus Gi over Li squared, okay? At this point, we can calculate the derivative of f with respect to time. The derivative of f is by construction made of the derivatives of Ci. Okay, so the integral between 0 and a of Gi derivative of f with respect to time integrated over x is simply a divided by 2 times the derivative of Ci with respect to time. Then we have to calculate the second derivative. You remember what we do is we have this equation, and we have to express this equation as a Fourier series. Okay, so we express f as a Fourier series, and then we integrate over space. This is why we have these integrals over space. So we have the integral of df over dt that comes from the left-hand side here. And then we have the second derivative with respect to x on the right-hand side that we have to calculate now. And we do it by parts. When we do it by parts, we obtain the second derivative of g, of course. So it turns out to be this. Minus a over 2 times Ci divided by the square of Li. And finally, we have the contribution of the optical generation. So we have to calculate an integral of this. This has no Fourier series because, of course, there is no unknown. This is given, okay? So we simply take the integral of this. We give it a name, as mathematicians do, okay? This is fully known because Gi is known as the cosine of x, Gs is a constant, and this is an exponential. So we call it alpha I. So we have reduced eventually the complicated equation that we started from to a simple equation that is completely separated. So we have to solve this equation once for each index I, but all equations have the same aspect, okay? And it is a first order equation in the unknown Ci, and Ci is the coefficient of the Fourier expansion, okay? So we have solved the equation by series. Also, in the coefficient, you remember we have Li squared, and then we divide by the diffusion coefficient. We have a time that we call tau I. The initial conditions are easy. Ci at 0 is just a constant, is the initial charge per unit area at 0, at time equal to 0 times 2 over A, okay? So the integration, there is some easy manipulation, and then we eventually find the excess concentration of the electrons, that is the original unknown of our problem, expressed as a Fourier series. So the series looks inconvenient, but it is not very inconvenient because we simply had to appreciate the value of these equivalent lifetimes. Okay, so Ti star, or the inverse of Ti star, is the inverse of the original lifetime of the electrons plus 1 over Ti. Ti, you remember, is defined earlier as Li squared over Dn, okay? So we simply have to understand whether we have gained something using this complicated solution, okay? So actually, we see that if we consider tau n as 10 microseconds, dn as, remember, we estimated the typical values of the diffusion coefficient, okay, 10 square centimeters over second, okay? So then we take these times T1, T2, sorry, tau 1, tau 2, etc. And we see immediately that when we increase the index, tau decreases, okay? So for instance, tau 1 is equal to tau 0 divided by 9, because we have I plus 1/2 squared in the denominator. Okay, so you see tau I depends on I, okay? That means that in the series that expresses this excess charge, the dominant term in this exponential is tau 0, okay? Because tau 0 is the longest of all times that we have here, okay? Tau 0 if you insert this value is tau n divided by 100, okay? So this is the fundamental message of all these analyses. If we build an MOS photocapacitor over using the epitaxial layer grown over a substrate that is heavily doped, we gain a factor of at least 100 in the sampling time, okay? So we reduce the sampling time very much, so the device becomes much more efficient, okay? So in itself, this concludes the analysis of the photocapacitor, but we must add some other consideration. You remember the photocapacitor is a very simple device. So there is no surprise in seeing that many of the complicated arrays of optical sensors are made of putting photocapacitors one near the other, okay, to build matrices or arrays made of photocapacitors. So at this point, it is convenient to talk a little bit about possible architectures that are used to build arrays of photosensors that are then the implementations that are used in cameras, cell phones, and whatever, okay, in the field of optical sensors. So the first implementation that we shall examine is a device that is called charge coupled device, in short CCD. The charge coupled device is a subclass of a larger class of devices that are called charge transfer devices, so CTD, okay? So the charge coupled device is a subclass of the charge transfer devices, okay? We shall also examine other types of charge transfer devices, okay? So in this very schematic implementation, assume that you have a one-dimensional array of MOS photocapacitors, one near the other, okay? The first observation is that in this implementation, the metal gates seem to cover almost completely the structure, so light can, in principle, could never get into the semiconductor. However, in these implementations, the gate contacts are not necessarily made of metals, okay? It is possible to manufacture the contacts in a way that they are practically transparent to radiation, okay? So assume that the contacts on the gates are transparent, so the radiation can enter the semiconductor. Another issue is that the gates are separated from each other and are independently controlled by applied voltages, but the gates are very close to each other, okay? So the distance between one gate and the next is kept as small as possible. Now observe how the gate voltages are connected. If you look from left to right, you see that gate 1, 4, and 7 have the same voltage that we call V1. Then gate 2, 5, 8 are connected to the same voltage that is V2 different from V1. And finally, gates number 3, 6, and 9 are connected to another voltage that we call V3, okay? Different from V1 and V2, and so on and so on. So this is called three-phase charge coupled device, and the applied voltages are also called, in this context, are also called phases. So V1 is phase 1, V2 is phase 2, and V3 is phase 3. these phases have an evolution in time, okay? And simply they go alternatively from a value that corresponds to the flat band condition to a value that corresponds to strong inversion condition. So each individual gate behaves like a photocapacitor. So now consider this situation. This situation is such that phase 2 is at high voltage, okay? Phase 1 and phase 3 are at low voltage. That means that under electrodes number 2, number 5, and number 8, we have a depleted region. So the depleted region has a boundary that is schematically shown by the thin line shown in the figure, okay? So during the integration time, some charge is integrated in these 3 photocapacitors, okay? For instance, photocapacitor the one on the left, number 2, has a stronger illumination, so there are more electrons in the inverted layer, okay? Photocapacitor number 5 has not so many electrons because the light at this position in space is weaker. And photocapacitor number 8 is somewhere in between, okay? Of course, light enters the semiconductor everywhere. So we also have an optical generation under all the other gates, number 1, 3, 4, 6, 7, 9, whatever. Everywhere in the material we have optical generation. But if you do not have the high voltage applied to the gate, in the positions where the voltage is corresponding to the flat band, there is no field, and the electron hole pairs that are optically generated simply diffuse away and recombine. Okay, so they do not contribute to the charge. Okay, so essentially, at the end of the integration period, we have packets of electrons that have formed under the gates in which a high value of the phase is applied. Qualitatively, you may understand these packets of electrons as associated to the amount of illumination that has come in those locations of the device during the integration time. Okay, so we have captured somewhat the illumination locally. Now the point is, how can we read these packets of electrons? Okay, the idea in the charge-coupled device is to use the phases to move the packets of electrons along the CCD and bring them to the, for instance, to the right end of the device and read them somehow with a reading device. Okay? So the issue now is to move the wave packets. To move the wave packets, instead of keeping the phases fixed in time, we start changing the value of the phases. Okay, so you remember when we were considering the previous figure, we were in a position in which V2 was high and the other two phases were low. So we were between this point here in time and this point in time. Okay, so here we had the integration time. Okay, now you can see that as time evolves, we put V3 high. We still have V2 high, and we still have V1 low. Okay, so for a while we have V2 and V3 high. That means that we are forming a space charge region under the gates that are corresponding to position to phase 3. So here, here, and here. Okay, I think I have another picture. So if you let me change here. This figure is more suited for understanding what happens. The names of the phases are not the same as in the other figure, but it is quite easy to understand. In this case, phase 1 is high. So at time T1, we have electrons under the gate attached to phase 1. Okay. Now, as time evolves, we increase the value of the voltage of phase 2 while keeping phase 1 high. So at time T2, that corresponds to the mid part of the yellow region here, we have that both phase 1 and 2 are kept high. So we open up a depleted region under the position on the right with respect to the original one. Okay, so we have an open region here, a depleted region with no charge. So the charge that was originally under phase 1 distributes equally in the region below phase 1 and phase 2. It distributes equally, okay? And the mechanisms are both diffusion and drift, okay? After a while, when the charge has been distributed equally, we put down phase 1. Here you can see on the right, we put down phase 1. So only phase 2 is high. So we eliminate the space charge region, okay, but we have a space charge region on the right of it. So we have a strong field, and the charges that were originally equally distributed below phase 1 and phase 2, all of them move to the right because we have put phase 1 off, okay? So at the end of these steps, we have been able to shift a packet of electrons originally in this position, we have shifted it one position to the right. Okay, it is for this reason that we need that the distance between the gates is minimum, because we need that a unique depleted region forms when we have two gates high nearby. Okay, if the gates were too far from each other, instead of having a unique depleted region, we would have two independent depleted region and no transfer of charge would be possible. Okay, so this is the charge transfer mechanism that takes place in the CCD. Okay, this also explains why we need three phases. Okay, if we have three phases, we can assure that the transfer is one directional. In this case of the example, the transfer is from left to right. Okay. If we had only two phases, well, if this gate was also phase 2, okay, when we open up phase 2 on the right, we would open up phase 2 also on the left. And the original charge we equally distribute to the right and to the left. Okay, so there will be no net motion of the electron packet along the channel of the CCD. Okay, so three phases are necessary to ensure that we have a one-dimensional motion of the wave packets. Sorry. This is the same as above, but after zooming back. So we have one charge under phase 1 here, but also another charge under phase 1 here. Okay, so you see that we can move simultaneously the charge packets from left to right, okay, in all positions of the device. Just to focus historically all these issues, the photodiodes and MOS phototransistors were introduced in 1967. And one may ask, why did they decide to evolve from photodiodes and phototransistors into CCDs? One of the reasons is the following, that if you manufacture an array of photodiodes or an array of photocapacitors or similar, okay, you must read the information of each optical sensor individually. So you must have, you remember, we were reading with some device that was mimicked by a resistor, okay? So if you manufacture an array of photo devices, you need one resistor per photo devices, okay? So you need many photoresistors, many reading devices, more generally, okay? It is impossible in practice to have that all reading devices are exactly equal to each other. They are slightly different, okay? So these differences in the reading devices introduces a noise, okay? If you instead consider an image sensor made of a CCD, where is it? Oh, sorry, I'm going the wrong way. Okay. If you consider a CCD, there is only one reading device that is, for instance, placed at the right-hand side of the CCD, okay? All charge packets are moved along the same channel and eventually they end up in the same position at the end of the CCD. So there is only one reading device. So this is much more preferable than having one individual reading device per pixel, okay? In this case, we have one reading device only for a complete array, linear array of pixels, which is much preferable from both viewpoints of the noise issues, but also for the occupancy of area on the chip, okay? So this is why at some point they kept investigating and they started manufacturing CCDs in 1970, okay? The gentlemen who invented them were Boyle Smith. They won the Nobel Prize for the invention of the imagers, okay? This is a picture of 1974. And now we have to look at possible evolutions of this architecture. Because obviously we would like to transform the linear array of the made of an individual CCD into a two-dimensional array, okay, in order to be able to detect a full frame, an image, a full frame of an image, okay? So in this page, you can see a possible method to transform a linear CCD into a two-dimensional CCD. So part one of the figure, this one, is again a cross-section of a linear CCD, okay? If you look at it from top instead of from the side, you see something like number 2, okay? So this is simply a CCD, a schematic of a CCD from top, okay? These arrows are impinging light, they mimic the light coming in. And this triangle on the right is the reading circuitry. Okay, so this is the place where the charge packets exit the CCD and are read and transformed into an electric signal. Okay, so the obvious idea to form a two-dimensional sensor is simply to replicate a number of linear CCDs in parallel. Okay, so you can see this arrangement here that is simply the replica of many CCDs in parallel. Okay, they have a problem. They have a problem. And the problem is that consider the integration time. Okay, in the integration time, the phases do not change in time. You have some gates that are operated at high voltage, so they have a depleted region underneath, and all the remaining gates are at the flat band condition. Okay, so nothing moves during the integration time. When the integration time is completed, it is necessary to transfer the charge packets into the reading device. Okay, and what we do is we operate on the gates in order to shift the wave packets in the figure here from left to right. Okay, this is the same in the linear arrangement and also in the two-dimensional arrangement. Okay, the issue is that when we shift the charge packets along the CCD, the light keeps coming in. So the optical generation does not stop during the transfer of the charge packets into the reading mechanism, into the reading device. Okay, so we have more and more optical generation that in some sense pollutes the existing packets because the generation occurs in the wrong position when the packets move. Okay, so the issue is we must transfer the packets as fast as possible into a region in which there is no light. Okay, so this region here is indicated by the gray area. So the gray areas, the horizontal gray areas, also are CCDs. They are simply the extension of the white part of the CCDs. The difference is that the gray areas are protected from the light. They have a layer on top that prevents the radiation to cross into the semiconductor. Okay, so what people do is they, at the end of the integration period, they operate very quickly on the gates and they transfer all the wave packets into the protected region. Okay, at this point, the region on the left is ready for another integration time. So they start another integration time on the left. And in the region on the right, they have to transfer the charge packets into the reading mechanism. And what is done is that you see all the packets that are at the right edge of the horizontal array are transferred in parallel into the vertical CCD. Okay, so by one clock pulse, they are transferred in parallel from left to right and enter the vertical CCD. Then the vertical CCD also has clocks. They are operated, okay, and the charge packets are transferred vertically, bottom up, into the single reading circuit. Okay, so again, we have only one reading circuit. So we have total uniformity of reading, no noise, and very little space consumed by the reading mechanism. Okay, so essentially in this architecture, the charge packets undergo a parallel to series conversion, okay, because they enter the vertical CCD and they are read bottom up. Obviously, the frequency of the clocks of the gates of the vertical CCD must be larger than the frequency by which we operate the horizontal CCD, okay? Because in this figure, we transfer 5 packets, because there are 5 rows, okay? 5 packets into the vertical CCD, and then we have quickly to transfer these 5 packets into the reading device, okay? So the frequency by which the vertical CCD is operated is, in this example, 5 times the frequency of the clocks of the horizontal CCDs. Okay, so more generally, the frequency of the vertical CCD is a multiple of the frequency of the horizontal CCD, and the multiplying factor is the number of lines of this architecture. So this architecture is not unique. There is another possible architecture that we shall see in the next hour. This is called frame transfer architecture. Frame transfer, because all the frame of the two-dimensional frame that has been integrated along the integration time is transferred all together into the protected area. So for this reason, it is called the frame transfer CCD. Okay. There is another advantage in this architecture, but we don't have time to illustrate it for the moment. So for now we stop, and we shall continue in 10 minutes. Okay, so before we consider the other architecture of a two-dimensional CCD, we must analyze a property of this architecture here. In the case where we want to apply this type of sensor to operate a display like a video screen or a computer screen or something similar. Any type of screen in which we have to present a succession of frames to be visualized one after the other in order to provide the illusion of motion to the user. You remember that if the frames are presented in a time distance that is shorter than about 50 milliseconds, the human brain has a retention of the image, it's so called, such that there is the illusion of movement. Instead, it is just a sequence of steady state frames that are presented one after the other. Typically, video screens or computer screens are scanned row by row. But there is another format that is also possible that is called the interlaced format, in which the rows of odd index, number 1, number 3, etc., are scanned first, and then this is followed by the scanning of the even index rows, okay? So this is called the interlaced format, and one can demonstrate that with the interlaced format, essentially one can divide the frequency of the frames by 2, okay? So it is a more relaxed situation with respect to the original one. So the need of a frequency band is smaller. So practically all screens use the interlaced format if possible. How can we implement the interlaced format when we are using a frame transfer CCD? This is very easy because simply during one integration time, we keep the gates, we operate at high voltage the gates of odd index. And in the next integration time, we operate those of even index. Okay, so we simply alternate the potential wells that are open or closed, and this automatically provides an interlaced format to the signal. So the interlaced format is obtained simply by changing the control of the clocks from one integration time to the next. Another advantage of solid-state sensors like this, not simply the frame transfer array, but of all solid-state sensors, with respect to the traditional implementation of video displays, is in the possibility of obtaining color signals. In order to obtain color signals, it is sufficient to use, instead of a single array, 3 arrays, one for each fundamental color, okay? Like red, yellow, and green. The incoming optical signal is split into the fundamental colors, and then each fundamental color is oriented into the direction of a different array. So we have 3 arrays that receive simultaneously the signals related to the 3 fundamental colors, and they have been obtained very simply because we can split the light by using a suitable optical prism, okay? We divide the colors from each other. And then the 3 fundamental color components are independently detected by the 3 arrays, and they are combined later into the signal, okay? So the implementation of it is very simple, much simpler than in the standard implementation of optical devices based on electron beams, okay? So now we have to examine the other possible implementation of the 2-dimensional optical device, optical sensor. So we go to this figure. And again, we consider first the linear array indicated on the left by number 1. The linear array is made of a set of individual photocapacitors that are the white things on the left. And as usual, these photocapacitors are operated alternatively during the integration time. So some of them have an applied voltage that is high and the rest is kept low, okay? So the photocapacitors integrate the charge corresponding to the optical signal. And then you see the gray strip, the thin gray strip that is placed vertically immediately on the right of the photocapacitors. That is a gate. By operating this gate, one can transfer the charge that has been integrated inside each photocapacitor, can transfer this charge from left to right into the vertical CCD. So the charge after integration is transferred in parallel into the CCD. The CCD is gray because it is protected from radiation. So the duty cycle of this architecture is very good because the transfer of the packets left to right is very quick. And after the transfer has been completed, the photocapacitors on the left can start immediately another integration period. Meanwhile, the CCD on the right transfers to the output circuit, so bottom up, the wave packets and the charge packets, and they are protected from the radiation. Okay. Of course, this implementation can be multiplied in order to achieve a two-dimensional arrangement. This is visible in the figure number 2. In this case, the individual sensors are oriented horizontally. So after the integration time has elapsed, the gate is operated and all the charged packets are transferred, in this case bottom up, into the horizontal CCDs that are protected from the radiation. Then the next integration time can start immediately. Meanwhile, the charged packets are transferred from left to right, from the horizontal CCDs into the vertical CCD. So also in this case, a parallel to series conversion of the packets is accomplished. And finally, the packets are shifted bottom up and eventually read at the reading circuit on top. Okay, so this arrangement is more efficient. It is called line transfer architecture. Okay, and is the other possible implementation of a two-dimensional sensor, optical sensor made of CCDs. Now we change the we go to the other set of slides. This is a replica of the transfer mechanism. Of course, there is a trade-off, as you remember. When we make a transfer of the charge, the transfer must be quick, okay? Because we don't want that the charge packets be polluted by the incoming radiation. But we cannot operate the clocks too quickly, because otherwise it may happen that some charge of the charge packets is left behind, okay? So there is, of course, a compromise between these two needs. And we have now to define the transfer efficiency and understand how we can make the transfer efficiency as big as possible. So the transfer efficiency is very easily defined, okay? So the if we call eta the fraction of charge that is transferred from one, here it is called stage. The stage is the depleted region under a gate into the next one, okay? Of course, some electrons are lost for each transfer. This is something that cannot be avoided. So if eta is the fraction of charge that is transferred, and of course this eta is expected to be smaller than 1, then we call it 1 minus epsilon, and epsilon is the charge transfer inefficiency, okay? This inefficiency may be small, but the issue is that the inefficiency accumulates, okay? If we have 1,000 gates in a single array, the inefficiency of each individual transfer combines, and we have to account for the inefficiency accumulated in about 1,000 transfers, okay? So if you look at the table below, that shows the typical situation in a CCD, in a two-dimensional CCD image sensor made of an array of 1024 times 1024 gates, okay? You see that if eta is 0.999, which seems very good, actually what you collect at the end of the CCD is just 0.13, more or less, of the charge. So you're losing very much. So in order to have a reasonable fraction at the output, like 0.98%, one needs a transfer efficiency of 0.99999. Okay, so something 10 to the sixth, 10 to the minus sixth in efficiency. An example, okay? Inevitably, in the depleted region that appears under two consecutive gates, okay, there is this type of shape, okay? This introduces a field that is called the fringing field, okay? Of course, this is a negative aspect for the transfer efficiency, okay? And there are some tricks that one can play to destroy the fringing field. For instance, to have one of the gates overlapping the other, like in the right-hand part of the figure, okay? Or decreasing the dopant in the substrate in order to have a more extended space charge region, okay? We go back to the other set of slides. And now we examine another type of charge transfer device. Charge transfer device of this type is called CID, charge injection device. So in part one of the figure, we examine the individual pixel of a charge injection device. This is different. The principle is similar to that of the CCD, but the final operation is different. Consider two photocapacitors, one near the other, and they are operated independently. So the photocapacitor on the left is operated with the gate clock that is called VH. H stands for horizontal, we shall see why. And the other one is operated with another gate voltage that is called V sub V. V stands for vertical, okay? Qualitatively, we have four possible combinations of voltages, okay? One combination is the one visible in part one of the figure. That is, the voltage on the right is high and the voltage on the left is small. So we have a space charge region under the gate on the right. Radiation is coming in, so we have an inverted charge under the right gate, okay? Now, assume that we apply the second combination at this moment. So we put VH also high. So we have two voltages, the left and the right voltages, that are both high. And as you remember, in this way we succeed in forming a unique potential well underneath the two gates, and the inverted charge distributes uniformly between the two, okay? Then in the next stage, we keep the left voltage high and we put the right voltage low. So in this case, of course, the charge that was uniformly distributed between the two gates shifts to the left, okay? In principle, we can repeat this operation several times. So it is possible by operating on the two gates, it is possible to shift the charge packet from right to left and vice versa, more than once, okay? If we want to read the wave packet, sorry, the charge packet, we put both gate voltages low. So as in the normal, there is no field that keeps the inverted charge near the interface, and the inverted charge will diffuse into the bulk and will produce a current that is readable by some reading device, okay? Can we replicate this architecture in order to form a two-dimensional array? Yes, and this is shown in part 3 of the figure that shows a top view of an array of charge injection devices, okay? So each pair of gates is now seen from top, and now you can see better how the gates are connected. All the gates that are on the right in the same row are connected together. And each set of connected gates of the same row goes to the right into the vertical control. At the same time, of the pairs of photocapacitors belonging to the charge injection device, those that are on the left and belong to the same column, they are connected together and they are operated by the horizontal control, okay? So now assume that all gates are kept high. So we are integrating during the integration time a charge, and this charge will equally distribute under each pair of gates during the integration time. If now we want to read one individual pixel, assume that we want to read the pixel that is upper left, okay? So we operate the vertical control of the first column to low, and at the same time we operate the vertical control of the same row to low. That means that pixel up left, number 1 upper left, will have both gates to low voltage, so its charge will be pushed into the substrate, will diffuse into the substrate, and will be read by the reading device. Okay. At the same time, all the pixels that are in the same first row, but they're not the first one on the left, so number 2, 3, and 4 of the first row, will have the left gate low, but the right gate will be kept low, but the left gate will be kept high. So they will keep the charge under the left gate. Similarly, all the pixels that are in the left column, the leftmost column, apart from the first one on top, will have the right gate kept high and the left gate kept low. So they will keep the charge under the right gate. All the remaining pixels will have both gates high, so they will retain the charge. Okay, so this architecture is very efficient because it allows one to address individually each pixel, and the charge of the pixel that is being read will be injected into the substrate and read at the same reading device. So there will be also in this case a single reading device, and the pixels can be individually accessed. So this is a very efficient architecture. We can make an observation that the reading operation destroys the information. This is true for every type of optical device that we have examined so far, because the reading operation in a photocapacitor or in a CCD or in a CID consists in injecting the charge into the substrate. So that charge cannot come back, it is lost. So after reading, we lose the information. Can we make it better? Reading without losing the information? Yes, we can. And this is done using the architecture that is shown in part 2 of the figure. In part 2 of the figure, we have the same two gates as before with a form that is slightly modified, okay? And in between, we have another gate. And you can see from the figure, the gate in between is somewhat underneath the other two gates, but it is connected with the gate of an MOS transistor, okay? So you see that this intermediate gate is not connected to any voltage generator, okay? The part that is below, it's inside the gate oxide. And the part that comes up above is connected to the gate of a transistor, so it is also inside the gate oxide of another device, okay? So this intermediate gate is not connected to any generator. That means that the value of the electric potential of this gate is determined only by electrostatic induction. So it is determined by the situation of the other potentials and charges that surround this gate, okay? This gate is called, as you may know, floating gate, because it floats. The potential is not prescribed by a direct connection with the generator, okay? So now assume that we are operating the CID as described before. So we start with an inverted layer present under the gate on the right. Then we put the gate on the left to a high voltage, so we equally distribute the charge. Then we put the right gate to low, so we force the charge to shift completely from right to left, okay? And in this step, we have not lost the charge. The charge is still available. It has simply gone from right to left, okay? But this charge has passed along the channel under the floating gate. So this charge, by electrostatic induction, has changed the electric potential of the floating gate. But the electric potential of the floating gate is also the electric potential of the gate of the MOS transistor on top. So assume that before the transfer of the charge, the floating gate was low, so the transistor was off. And when the charge crosses the channel, the floating gate goes high and switches on the channel of the transistor. So we can read a signal in the transistor just because the charge in the CID has made the transition from right to left or vice versa. So we have associated a signal, that is the signal that goes through the MOS transistor, without destroying the charge in the CID. So this type of reading is a non-destructive reading, okay? And of course, it can be repeated. After one passage from right to left, we can do another one from left to right, as many times as we wish. So we can even average the result of all these signals and try to eliminate the noise, okay? And the floating gate operation is incredibly efficient. There have been experiments in which it was possible to detect a very, very small charge packet, and also the loss of electrons in one transfer from left to right or right to left was detected to be less than 1 electron lost per passage, okay? So it is an incredibly efficient method to read the charge. So we have achieved the non-destructive reading of the charge thanks to the floating gate operation. So this architecture of the CIDs is really very efficient and very widely used in the applications to optical sensors. What is the working operation of a floating gate? Okay, it is easily understood because consider only for a second, consider only the gate on the right. We have a gate with some voltage applied to it. Then we have an oxide layer between the upper gate and the floating gate. So we have a capacitor, and this capacitor is linear because we have two pieces of metal and the oxide in between. And then from the floating gate to the semiconductor, we have, as you may remember, the capacitance of a gate that is the series of the capacitance of this other oxide and the capacitance of the semiconductor. Okay, so essentially we have three capacitors in series instead of two, and two of them are linear. Okay, so if you want to draw schematically, I don't rotate the figure because I need the other figure for the moment. Okay, we have the series of three capacitors that are the upper capacitor that we call Cu, the lower capacitor that we call Cl, and the semiconductor capacitor that is we call as usual CSC. Okay, so the upper capacitor is the one between the upper gate and the floating gate. Of course, the region of the floating gate, this piece of metal, has no charge in it. Okay, we assume that during fabrication no charge has been introduced by mistake into the floating gate or into the oxide around it. Okay, the interface of the semiconductor is a place in which we have the crossing of the charge packet from left to right or vice versa. So the interface is a position in which we are injecting the charge. Okay, and of course when we inject the charge we modify the value of the surface potential. So if we now go to the figure of the circuit and rotate it, we see something like this, in which at this position here we inject a charge. By injecting the charge, we modify the value of the surface potential phi s. And of course, we modify also the value of the electric potential that is indicated with Vf prime. Prime is because, as usual, we refer the zero not to the bulk contact, but to the asymptotic part of the semiconductor. Okay, so it is V prime F is like Vf minus V of flat band. What is V prime F? It is the voltage of the floating gate, meaning that the voltage of the floating gate is also the voltage that goes into the gate of the MOS transistor. So it is the voltage that controls the transistor. Instead, Vg prime is prescribed. It is high, okay, it's beyond strong inversion condition, and Vg prime is fixed. So the problem of the floating gate is that we want to calculate how much Vf prime changes when we change the charge at this point, okay, at the interface. These two capacitors, Cu and Cl, they are linear. So we may call Qu the charge per unit area that is present in the upper plate of Cu, minus Qu is the charge per unit area in the lower plate of Cu. Ql is the charge per unit area in the upper plate of Cl, and minus Ql is that in the lower plate of Cl. On the other hand, we assume that in the floating gate, there is no charge. Okay, so the floating gate is globally neutral. Okay, so obviously QL is equal and opposite to minus QU. So QL and QU are equal to each other. This area that I'm indicating with the mouse is the floating gate. So it is the block of metal that is indicated as floating gate in the other figure, okay? It is globally neutral, there is no charge in it, so QL and QU are equal. Of course, the calculation can be repeated also in the special case in which, for any reason, there is a charge in the floating gate, but in this case, there is no charge in the floating gate. Now, the calculation is relatively easy. Using the simplified formulas, we have that the inversion charge. This is the charge packet that crosses the interface from left to right. So when it is present under the floating gate, we have this relation between Qi, Vf, and phi s, okay? Remember, the purpose is to find Vf as a function of Qi, okay? Then you remember QL and QU are the same. So QU is the charge that belongs to, you may think of it as the charge that belongs to a series of two capacitors, okay? Cu and Cl, okay? So we may write Qu as the expression of the series of the two capacitors. You remember, of course, this is the series of the two capacitors, times the voltage drop corresponding to the two capacitors, that is Vg minus phi s, okay? But this Qu is also the charge in the upper capacitor, so it is Qu times Vg minus Vf, okay? So we have this equality. Then we extract phi s from this equation. Phi s is a linear combination of the floating gate voltage that is unknown and Vg. From this equation, we can also extract the drop Vf minus phi s. So Vf minus phi s is replaced here Vf minus phi s. And the square root of phi s goes into here. Okay? So, conclusion, we have a connection between the floating gate voltage, Vf, and the charge, Qi, okay? How do you exploit it? Vf is the floating gate voltage that operates the transistor. So by detecting the current in the transistor, we can calculate back the floating gate voltage, and from this formula, from the floating gate voltage, we can calculate Qi. Okay, so we extract an information directly concerning the amount of charge that has been integrated during the integration time, without destroying the charge itself. In this equation, R is just the ratio of Cu over Cl. So R is given. Okay, so this is how the floating gate operates. Okay. Until now, we have considered a number of applications of photodiodes, photocapacitors, CCDs, and CIDs as optical detectors, okay? Which is actually the major application of these devices. However, in the past, people have tried to think of other applications of some of these structures. In particular, people were thinking of other applications of CCDs, okay? One was application to solid-state sensors. But another application is, for instance, why don't we use the CCD as a memory? We can associate an empty charge packet to a logical zero, and the field charge packet as a logical one. Of course, we do not fill by impinging light, okay? If you want to realize a memory, you have to fill the charge packets electrically from some injection device from the left, okay? So if you fill the well, you have a 1. If you don't fill the well, you have a 0. That's easy, okay? Actually, they tried to implement memories, but that was not so successful. The other architecture of memories that you have seen in other classes have been much more successful than this, okay? So applications to memories were not successful. Another possible application that we shall discuss on Thursday is this. You see, a CCD can be understood as a delay line. It's a device in which you make charge packets to flow, for instance, from left to right, and each of them moves by one step in some time, okay? So it is like a delay line. The same packets eventually will come out on the right after, say, 1,000 steps with a delay of 1,000 times a specific time, transfer time, okay? And the question is, can we exploit a delay line for something else than optical sensor. For instance, for manipulating a signal. The answer is yes, and it is very interesting and also very elegant. Okay, so we stop here, and we shall start with this application on Thursday. Okay, thank you.